There are numerous games that give speed boosts by going through rings of some sort. I want to investigate what it would take for such a thing to be made in real life, but with a coil gun in place of the ring. This is essentially known as a coil accelerator. However, modern day coil accelerators mostly deal with accelerating small projectiles. It's hard to find any examples of any large scale coil accelerators where the length to radius ratio is small. This makes me think that it's either not practical or just not very popular. But having a practical large-scale coil accelerator could be very groundbreaking, assuming they are able to generate enough force to accelerate objects through it. The objects passing through would no longer need to carry a propulsion system, but rather just need to be made of or carry a certain amount of ferromagnetic material. To investigate the practicalities of a coil accelerator, first let's take a look at the theory behind how they work. When a wire is subjected to a current, it produces a magnetic field around it. This magnetic field can be found by using the right hand rule, where your thumb points in the direction of the current and your fingers curl in the direction of the magnetic field. The higher the current passing through, the stronger the magnetic field. The problem is that the magnetic field strength is inversely proportional to the distance away it is from the current. This is the biggest limitation our large radius electromagnet will face. A coil gun works by having a long wire wrapped around in coils, amplifying the magnetic field because of the turns of wire contributing to one another. To measure the magnetic field, we can use Biot-Savart's law here. From this equation, we can integrate along the path of this line integral, and when we do that, we can find that the magnetic field intensity at the center of the coil is going to be this. From here we can see that the strength of the electromagnet is going to be inversely proportional to the radius of it. That means that we will need to either increase the current, the amount of turns in the wire, or the amount of ferromagnetic material passing through the accelerator to combat the large radius that our accelerator will be. Also, we can't use Ampere's law for this because of the small length to radius that our coil gun will be. I used a software package that uses finite element analysis to find the force versus position data of the rod as it passes through the coil gun. You can see here as it iterates through the trajectory of the rod, calculating the force along the way. I also used it to find the magnetic field around the coil gun, seen here. Okay, so now that we have the force with the position data of the rod as it's fallen through the coil, we're going to need to derive an equation for its velocity with respect to its position. We need to approximate the integral with respect to dx on this side, as we only have the magnetic force as a matrix of the position. So we'll end up with this equation. I can go ahead and throw this equation into a MATLAB program to solve for its velocity. Here I'm comparing the velocity of the rod during free fall with the velocity of the rod in a magnetic field, and the results are disappointing. I really see barely any deviation in the velocity with the rod in the magnetic field, but this is probably due to the fact that I only have 1 amp running through the coils and only so many coil turns due to the limitations of my equipment. The process of designing the accelerator started with wrapping a 24 AWG 800-foot insulated copper wire around a roll of tape 11 centimeters in diameter. Coil accelerators need a way to switch off the power after the rod has passed the center of it, or else the electromagnet will pull back on the rod. This was done using an infrared phototransistor with an Arduino controlling the switch. After the rod passes through the infrared gate, the Arduino turns off the power, as well as measuring the velocity of the rod as it passes through. A 120-tip Darlington transistor is used to flip the power off. The rod used is a ferrite rod with a relative permeability of 200. Here you can see a side-by-side comparison of the rod being dropped in free fall with the rod being dropped with the coil accelerator on. The demonstration shows that the theory and measurements were correct. It's hard to tell without having the proper equipment what such a thing would look like scaled up, but it's easy to see that problems such as saturation of the ferromagnetic material, heating of the wires, or just sheer cost of the thing might be the limiting factor.